Laura,
George,
what are you doing?
I'm enjoying life over here. What are you
Are you
doing?
really?
I
I tell you
am.
what, man. I mean, and when people use exclamations in their, in their backgrounds and in their text, it seems that they're excited. So there's like, you're happy about N, right? Because you got
I
N.
am.
Are you? Why is that? What is that?
I'm happy about n factorial.
Are you really?
I am. Are you familiar with n factorial?
I think that like if I had said if like n was 10 and I said n factorial, I think that that's how many different ways I can arrange those 10 distinct objects in a row, right?
Absolutely.
Permutations, I think, yeah.
Mm-hmm.
But then you got some other business under there with what K
Yes, if
factorial
you
n
can.
minus K factorial. Yes, that's right. Hey, maybe we'll be able to do the weather in a little bit by showing, oh, I could do the weather. We have a sunny day today. Or sunny
Love it.
evening.
It's very rainy here in Southampton. I did get caught in the rain.
Oh,
So I'm loving your background, especially today.
yeah, that's fair. That's okay. And it's such a cheerful background too, and probably kind of useful, I imagine. So where might we see something like this?
Well, I was wondering, the point of me getting this up was I was wondering if you wanted to talk about distributions today. So maybe
All
we could
right.
use this in maybe a binomial distribution.
I think we do use that in a binomial distribution, right? Because that's the choose function, right? Like combinations of. Yeah, I think so. I think we could definitely use that. All right. So
Mhm.
binomial distribution. I guess we have certain conditions that, have to be in place for us to be able to say that we have a binomial distribution.
I would say so.
Binomial, right? That means what?
It's dichotomous, isn't it? It's either
Yeah.
one thing or the other.
Yeah, it's either one thing or the other. That's right. So either I make a free throw or I don't make a free throw. Either I like ice cream or I don't like ice cream, right?
Absolutely.
The reoccurring theme if people like ice cream or not, right?
Mhm.
So yeah, so I have some kind of a output, right? That's either a one or a zero, a yes or a no, something like that. So
Oh,
I may ask the question, right? Okay, if I perform some kind of a experiment, some kind of a trial that involves either a zero or one outcome, or a heads or a
mhm.
tails, or a yes or a no, maybe I can figure out if I do it a certain amount of times, what the probability is of getting a specific amount of yeses, right?
Absolutely.
So maybe a good example would be if I'm a 50% free throw shooter and I go up and I shoot 10 free throws and I make 7 of them, I'd be able to figure out what the probability is that I make 7 free throws out of the 10, given that my 50%, my percentage of making free throws is 50% or whatever percentage. It's consistent across every free throw that I shoot, and any one is independent of any other trial. So if those
Yes.
are in place, then I think we can use a binomial distribution to say, well, what's the probability I'm going to make 7 out of 10? If I'm going to make more than 7, if I'm going to make less than 3, or something like that, right? Does that make sense?
Absolutely. Yeah.
All right, let's see what that equation looks like. So we're going to be using some of the stuff that's behind there. They're behind you, but
Woo.
I think there's more stuff that needs to be thrown in there, right?
What sort of things would you have in mind?
Well, okay, so there's definitely going to be a probability. So we're trying to figure out the probability of a random variable x. I'm going to use capital X here for our actual random variable to denote the random variable. And then I'm going to use lowercase x for a specific value. So in our particular example, well, there's an n that's being talked about. So I said, I'm going to try 10 free throws. I may want to find out what the probability is. The amount of free throws I make happens to be 7. Okay, so I may
Okay.
be able to figure that particular probability out. Okay, so I believe, right, that this particular probability is going to take lowercase p, which p is, I'm going to say lowercase p is the probability of, let's say, a success, right? So making the free throw, let's say, n would be the number of trials. Okay.
Okay.
I think that's all we need. I think we need P, probability of making a free throw in our case. That would be, how many free throws am I going to make? I'm going to make lowercase x of them, right? Is that right?
Okay.
Okay. That means that 1 minus P is the probability of failure, right? So the rest, if I'm trying n, if I have n trials and x of them are successes, that means that
N minus x.
n minus x are the failures, right? So that means that the failure, probability of failure, which is 1 minus p, that's going to be looking like we raise that to the n minus x, right?
Cool.
But there's certain instances though, where, like, if I, as an example, if I had a success, that's 1, 2, 3, that's 6 success, and then 3 failures, right? That's 7 successes, that's 3 failures. I can have the same exact situation by rearranging these particular values. So if I had F, then a couple of S's, then another F, then some more S's, then another F, and then the rest of those S's, however many I need, 1, 2, 3, 4, 5, 6, 7.
Got it.
These two represent exactly the same outcome,
Sure.
right? So I have to allow for however many different combinations I have of those particular values in different orders, basically. So that's where that bit behind you comes in.
Absolutely.
Which is combinations, and I think we can write it this way: combinations of n taken x at a time, where n, x, the combinations of n taken x at a time is simply, thank you, n factorial over, God, straight to the rescue.
Darn it, I can't lie down enough.
I don't want you to fall out of the picture. Get back there. Okay, I got it.
Okay.
Was it K? I screwed it up with the K. Hold on.
It's all right. This formula behind me is using K, but we're using X.
Yeah, we're using X. So let's change that to X. All right. You try to trip me up on that. I see how you are.
I did it deliberately.
So, did you? Well, it worked. Man, you want me not to look bad? You want me to look bad in front of everybody? I don't blame you. I don't need help on that. I can look bad on my own. All right, so this is what we're going to be doing. We're going to be using this to figure out what those probabilities are going to be for x equals 0, because you can make none of them, for x equal 1, for x equal 2, and so on. Okay, so maybe we can use Excel to actually set up a nice distribution using this formula, or maybe they have a specific formula, right? So maybe we can put it in because, we want to show off and put it in, from scratch, or we can use the binomial distribution function. What would you have me do? What would you do? I imagine you would show off.
I'm all about the showing off.
Are you? Okay, cool. Oh, this is something that we did previously, isn't it? All right, let's. Oh. That looks familiar. That was the birthday problem. All right, let's do another one here. Okay, so let me make this kind of big here for the ongoing saga of stats and maths with Laura and George. Saga. All right, so again, we're going to say, all right, we're going to label what n is, because n doesn't change. That's the amount of trials. So let's say for our case, it's 10. Okay. Let's do a probability of success. So we'll call it lowercase p. We'll say that that for right now is 0.5. Okay, not a very good free throw percentage, but that's okay. We'll say that x represents how many successes I can have. So the smallest amount of successes is how many?
Well, if it's n equals 10 and p equals 0.5, then x will have to be 5. Is that?
No, what
Oh, have I missed?
that's the average, I think, right there. 5 would be what we're expecting.
My apologies.
That's okay. That's okay. No need to no need to apologize. Let me rephrase the question.
Sure.
If I'm shooting 10 free throws,
Mhm.
what's the smallest amount I can make?
0?
Yeah, that's right. I know. I know
Okay.
it's hard to believe that I'm not going to make any, and probably the probability will show that. But the next amount I can make is 1, right?
Sure.
So this binomial distribution, the values that we can get are from 0 all the way up to 10, correct?
Yes.
So our x values are going to go from 0 to 10. So let's do that. And now the probability of getting that particular value of successes, I'm going to denote by the capital P, open parenthesis, capital X equals lowercase x. Okay, so the lowercase x's are the ones in the column right next to it that we're going to be referring to. So we said we wanted to show off, right?
Absolutely.
All right, whenever we get a chance to show off, we take advantage of that. Okay, so here we're going to have equals, and let's actually use the formula that we talked about. I think the first bit would be combinations, right?
Okay.
So I think if I start typing COOM, yeah, combinations. Okay. The number, so number is a total amount that I'm actually, how many trials I have. So that's going to be 10.
Okay.
Okay, so now if I'm going to use the fill, the fill feature here, I need to make that an absolute reference.
Okay.
Okay, so that means that I think I just hit F4 and it puts $ in front of that cell reference. So it knows to go to that one. You know, it knows to go specifically to that one, no matter, you know, how many cells I draw it down. If I don't make an absolute reference, that particular reference will move down as I'm using the copy function. So this
we don't
puts
want
it in
that.
cement, I guess you can say, right? Comma. Number chosen is our x value. We're going to leave that. We're not going to put an absolute reference on it because we want it to change as we copy it down, right?
Sure.
Close that parenthesis. That's the first bit.
Nice.
Now we need P, right? So times, I think we have to put times in because it's not implied. This value, again, make that an absolute reference by hitting F4. Okay. That's going to be raised to the.
Now, was that x?
Yes, it's exactly right. X, again, leave that as we're going to leave that one as a relative reference. So it'll be able to copy down. It'll change its position. Times, what was it?
It was 1 minus p.
Open parenthesis, 1
yes.
minus P. Again, F4, because that's not changing. That P value is not, that lowercase p is not changing. That close that, raised to the.
No, I think we're going to need an open bracket here because it's n minus x.
N, which is always 10, again, F4, minus.
That would be G4.
All right, that is showing off.
Love it.
Me too. There it is. Okay.
Hey.
I love it too. All right. Okay, so now when I copy this down, it's right in the middle. So 0.5 right out of 10. So is there
Mhm.
something you might want to predict is gonna happen with these numbers? Some kind of special type of form they may take? It's a very vague question.
Perhaps they would sort of, the higher probabilities would be towards the middle, and towards the outside would be a lower probability.
Yes, something more. I'm going for something more. Some extra bit that makes it look nice.
Would it follow the binomial distribution?
It will follow the binomial distribution, but when we lay it
Mhm.
out, I'm kind of giving a little bit of a clue there.
Ah,
I think it's going to be nice and symmetric.
let's find out. Hey,
We never get tired of being right, do we?
absolutely not.
Never. So now let's actually see. This is kind of cool. Might as well do this. If I highlight those and I insert, let's insert a scatter plot. I like scatter plots for some reason.
Okay.
I'm going to include a scatter plot. Okay, let's move it off to the side here
Look at that.
a little bit. Look at that. It's symmetric, isn't it?
It is.
Looks like it. What if I change this p-value here to 0.7? What's
Ooh,
going to happen?
let's find out.
No, I want you to predict it.
Darn it.
Yeah, I'm sure you're going to do it correctly. Come on, how are we going to build our confidence?
Would it be a little bit more leptokurtic, would you say?
Say that bit again.
Leptokurtic? Is it?
What? That's a fancy word that I don't know what that means.
Oh, sorry, I'm talking about the kurtosis.
No. You're talking about like, yeah, I think you're right. It's going to do what to it? Let's put it in terms that I can understand.
So the tails are going to be very slightly flattened, but the middle bit is going to be more raised.
It's going to be more raised. What about its position? Because now it's centered about what?
Well, it was centered around the middle.
Right.
Would it be a little bit more skewed?
It is going to be skewed, isn't it?
Okay.
It's going to be skewed. So the kurtosis is kind of telling us what how do you call it? The tails are compared to the peak,
Yep.
like the curvature. Okay. This, I think, deals with the skewness. I think it's going to move it
I
left
see.
to right, right?
Okay.
What do you think it's going to move? Before it was 0.5. Now it's showing 0.5. But when I hit enter now and it takes 0.7 as a probability, it's going to move which way?
The peak is gonna move to the right. Hey, there we go.
Beautiful. Beautiful. See that? Awesome.
I mean, what this graph is showing you is that there is zero probability of you failing. Is that correct?
Very little probability. In fact, a very small. Yeah, we're looking at
Look at that.
0.5 zeros and then a 5. So yeah. So if I'm 70% free throw shooter and I go up and shoot 10 free throws and make none of them, there's probably something else going on.
Mhm.
Right. Okay. So how was that?
That was pretty good.
All right, cool. So maybe next time, actually, let me stop the share here. Maybe next time we can talk about another discrete probability distribution.
Sure.
Do you know of any?
I know of the Poisson distribution.
That's
Should we use that one?
cool. Yeah, maybe we'll do that one. Maybe we'll do that one. All right, so people are gonna have to tune in to see.
Until next time then.
Until next time, Laura, I'll talk to you soon, okay?
All right. Thank you very much for today.
All right. Take care.
You too.